In the previous video, we learned that DNA can become supercoiled. But how do scientists describe the topology of DNA mathematically? They use three related quantities: linking number, twist, and writhe. Let's begin with the linking number. DNA can exist as either a linear molecule or a closed circular molecule. In linear DNA, the free ends can rotate, allowing twisting stress to be released. However, in a covalently closed circular DNA molecule, there are no free ends. As a result, the two DNA strands remain topologically linked and cannot be completely separated unless at least one strand is broken. This topological relationship is described by the linking number. Linking number is the total number of times one DNA strand is linked with the other. Another way to think about it is this. If you wanted to completely separate the two strands without breaking them, the linking number tells you how many times one strand would have to pass through the other. The linking number is made up of two components, twist and writhe. Twist measures how many times the two DNA strands wind around each other to form the double helix. In other words, it counts the number of helical turns in the DNA molecule itself. And writhe measures how the entire DNA double helix coils or crosses over itself in three-dimensional space. If the DNA lies flat without crossing over itself, the writhe is 0. But when the DNA forms loops or supercoils, the writhe changes. These three quantities are related by a simple equation: linking number equals twist plus writhe. Let's see an example. Suppose a circular DNA molecule has a twist of 5 and a writhe of 0. Its linking number is therefore 5. Now imagine the DNA coils around itself so that the writhe becomes -3. Since the DNA strands have not been broken, the linking number cannot change. Therefore, the twist must increase from 5 to 8. This shows that twist and writhe can be converted into one another while the linking number remains unchanged. So far, we've learned what linking number, twist, and writhe represent. But these quantities can also be positive or negative. Let's begin with twist. DNA normally exists as a right-handed double helix, so its twist is considered positive. If the helix were left-handed, the twist would be negative. Now let's look at writhe. When the DNA axis coils around itself in a right-handed direction, the writhe is positive. When it coils in a left-handed direction, the writhe is negative. So far, we've learned what linking number, twist, and writhe are and how they are related. But writhe itself can appear in different structural forms. The first is interwound, or plectonemic writhe, where different regions of the DNA double helix wrap around one another, much like a twisted telephone cord. The second is toroidal writhe, where DNA wraps around another structure, such as histone proteins in eukaryotic chromosomes. Although these structures look very different, both contribute to the writhe of a DNA molecule. Now that we understand the three components of DNA topology, let's see how scientists determine whether a DNA molecule is positively or negatively supercoiled. We first need to know what the DNA would look like in its relaxed state. In bDNA, one complete helical turn contains approximately 10.5 base pairs. Therefore, the relaxed linking number can be estimated using this equation. We can now compare the actual linking number with this relaxed value. The difference between them is called the linking difference. If delta LK is negative, the DNA is negatively supercoiled. If delta LK is positive, the DNA is positively supercoiled. To compare the degree of supercoiling between DNA molecules of different sizes, scientists use superhelical density, represented by the Greek letter sigma. Superhelical density provides a normalized measure of DNA supercoiling, making it possible to compare different DNA molecules regardless of their length.